In this lecture, we will talk about different properties of homography. So, let us summarize what are the features of a projective transformation. We know that a transformation is projective. First, it has to be a mapping from a two-dimensional projective space to another two-dimensional projective space. Then it should be invertible and collinearity of every 3 points to be preserved, that is 3 points, for example, x 1, x 2, x 3, which lie on a straight line. Then after transformation, transformed points also should lie on a straight line. And also we have discussed that there is only one form of this kind of transformation, and that is in the form of a non-singular 3 cross 3 matrix. So, let us consider a typical case of this projective transformation, a kind of a schematic diagram by which we can explain these properties. So, you consider a projective space, two-dimensional projective space, and you can see that O is the center of projection and a projection plane which is in the canonical form is placed at a distance 1 along the z axis of this particular projective space. And let us consider another projective space in the same representation, similar representation, but it has a different coordinates of the center of projection. It has different orientations of the coordinate axis, and also accordingly with respect to that its canonical projection plane is also defined. So, a point in this case O prime is the center of projection of the other projective space. So, a point in the in the projective space which has been shown earlier, that is represented in this form. We know that any point in the canonical space is represented by a ray connecting to the center of projection, and whereas a point in the transformed space that is also represented in this form, and here we are showing that there is a mapping between the point P and between P prime. So, there is a mapping, and that mapping is defined by a transformation matrix, 3 cross 3 transformation matrix, as we have discussed earlier, and this is how we denote a projective transformation. We can visualize the projective transformation. For every point in this space, there will be a unique point, another unique point. Every point in this space, there will be another point in the transformed space where it will map to that particular point uniquely. So, to summarize this property, also we can say that if the point lies on a, if there is a straight line and if the point lies on that straight line, so that straight line also, so all the points in that straight line, if we map them, they will also form another straight line, and in that straight line all the mapped points will lie. So, we can say there is a mapping from straight line L to L prime under this transformation. And we have also discussed how this transformation is related, how we can derive the transformed points or transformed straight lines from the points or straight lines of the original projective space. So, the relationship is that for straight line we have to apply the transformation matrix, which is transpose of the inverse of the transformation matrix for point transformation. So, the relationship can be summarized in this form, that for a point if I multiply the point x in the projective space representation, which is an homogeneous coordinate representation, if I multiply it with a 3 cross 3 transformation matrix H, then we will get the corresponding transformed point also in the homogeneous coordinate representation. Similarly, for a line, if we multiply it with the H minus T matrix, which is transpose of inverse of H, then also we will get the corresponding transformed line. So, let us discuss again that how vanishing points they are related in the transformation in the transformed space. So, in this case we have drawn a pair of parallel lines and one of them is denoted by L. Consider L is transformed in the transformed space by a line L prime, and we know how L and L prime is related. So, you multiply L represented in a 2-dimensional projective space by transpose of inverse of this matrix H, and then you can get the corresponding transformation of L prime. That means, you have to multiply L with H minus T. Similarly, if I transform the other point of that parallel line, we will get another straight line, and this straight line incidentally we will observe that though they are parallel in the original projective space, but in the transformed space they will be appearing as a converging straight lines, or actually they will intersect at certain points. Now, this point is called the vanishing point of these straight lines. So, the interpretation of this vanishing point in the transformed space can be very easily given if we understand that what is the intersection between these parallel lines in the original space. We know that we have already discussed that when two lines are parallel in a projective space, they intersect at a point which is at infinity, but there is a finite representation of that infinite point. And in this case, for example, if we represent the straight line by this equation a x plus b y plus c equals 0, and then the all lines parallel to this straight line will intersect at a point in the projective space, which can be represented by the coordinate b minus a 0. That is a homogeneous coordinate representation. So, the ray connecting this point and passing to the origin, that same ray is representing this element, and we know that this point is also called ideal point. Now, the vanishing point of these parallel lines in the transformed space is nothing but the transformation of this ideal point into this space, which means if I apply transformation matrix, if I multiply transformation matrix with this point, then I will get the vanishing point. So, what we can get is that we have to represent the intersection point of the parallel lines in the original space, which incidentally is b minus a 0. This column vector represents the intersection point for a line for all parallel lines which are parallel to the line a x plus b y plus c equals 0. So, if I multiply it with h, then I will get the vanishing point, corresponding vanishing point, that means the corresponding coordinates of this point in the projective space with this computation. So, this is simple interpretations of a vanishing point, and that is what we have represented here. Now, another interesting part is that we know that if I take any other parallel line in the original space, any other set of parallel line in the original space, suppose you take another set of parallel lines in the original space, and then if I transform these lines in the projective space, they will also meet at some vanishing point, and all these vanishing points they lie on a particular line which is called vanishing line. So, how do you get this vanishing line also in the transform space? What is the representation? So, there we know that all the vanishing points in the original space they lie on a particular line, which that line is called line at infinity, and that is given by the this representation 0 0 1 in the, let us say that is an element in the projective space representing the all the straight lines. So, this vanishing line is nothing but the transformation of this line at infinity into this transformation space. So, which means that if I perform transformation of line at infinity by following the same rule of line transformation, then I will get the corresponding vanishing line. So, let me find out this particular equation which is hidden by this particular hidden here. So, let me write it here. So, what we can do, we have to multiply the line at infinity represented by this from 0 0 1, then we will get the corresponding vanishing line, which is this line here. So, this is a interpretation of a vanishing point and vanishing line in the transformation space. So, just to summarize all these properties in the transformation space, or all the properties of this projective transformation or homography. So, we have these are the transformations those we have studied, that is point transformation, which means that we have to multiply a point in the projective space by the corresponding transformation matrix, then you get the corresponding transformation point in the transformed space. You should remember that all the representations are in the homogeneous coordinate form. Then line transformation, where a line has to be multiplied by the matrix H minus T, which is the transpose of inverse of transformation matrix, then you will get the corresponding transformed line in the transformed space. Similarly, for vanishing point, for lines parallel to, say, represented by this form A, B, C, that is the form of a line, then the vanishing points can be derived by multiplying the intersection point of those parallel lines in the original space with the transformation matrix, which would be B minus A 0, that is a typical representation of the intersection point of lines which are parallel to the line given by parameters A, B, C. And vanishing line would be the transformation of line at infinity of the original projective space, which is given by 0 0 1, and that has to be multiplied once again with H minus T, which is transpose of inverse of transformation matrix, and that would give us the vanishing line. So, let us consider an example by which we can show all these computations. You consider a homography matrix, which means this is a transformation matrix which is given in this form. You can say this is a 3 cross 3 matrix and which should be incidentally non-singular, you can verify that. So, the computational problem is that you have to compute the transformation of the line formed by 2 points given by 2 4 2 and 6 9 3, both the points in the 2-dimensional projective space. So, let us see how we can compute this. So, there are few methods by which you can do it. I will discuss 2 of them. So, the first method, in this method what we can do, that first you compute the transform points of 2 4 2 and 6 9 3. So, you get the corresponding transformation point in the projective space. So, it is figuratively I can show you. So, you have a projective space where you have these points say P and Q, and P is given by the point 2, 4, 2 and Q is say 6, 9, 3. So, you find out their corresponding transformation in the transformed space. Suppose this point is P prime and this point is Q prime. So, what you need to do? You have to perform the multiplication of transformation matrix H with P and multiplication of transformation matrix H with Q, then you get this point P prime and Q prime, those are the transformation point. Now, you compute the straight line in the transform space, which means if I perform P prime cross Q prime, I will get the corresponding transformation matrix. So, let me see these computations once again. So, first let me reduce the representation of these points. Since there is a scalar quantity 2, I can divide all the coordinates to make it more simple representations of 1, 2, 1, and similarly 6, 9, 3 I can make it simpler representation of 2, 3, 1. You could have performed using 2, 4, 2 and 6, 9, 3 also. So, it is just for the convenience of computations I have taken these two. Now, you transform 1, 2, 1 and 2, 3, 1. So, if I transform 1, 2, 1 by multiplying this matrix, then you will get this point 5 minus 1, 11. You need to check when you multiply it, and if I multiply 2, 3, 1, then you will get the coordinate 12, 3, 16. Now, what you should do, that you have to take their cross product to compute the transformed line. So, you perform the cross product of these two and you can find out that the result would be minus 49, 52, 27. So, that is the representation of the straight line, which means the straight line in our conventional coordinate form should be represented as 49 minus 49 x plus 52 y plus 27 equals 0. So, this is one of the method by which we have carried out these computations. Let me discuss the other method. So, in this case what we will do, rather first we will perform the computation of line in the transformed space. So, let us consider your original projective space and once again 2 points P and Q. So, you have to compute this transformation or you have to compute line between P and Q by performing the cross product of these 2 points in the homogeneous coordinate representation. Now, you perform the transformation of this line, and in this case what you should do? You should multiply with transpose of H inverse of this matrix, inverse of this transformation matrix, which is represented as H minus T. So, if I perform this operation, then I will get the corresponding transformed line in the transformed space. So, L prime should be equal to H minus T into L. So, this is the computation we will be carrying out. So, let me detail out this computation. So, first we will be computing the cross product of these 2 points and the line would be minus 1, 1, minus 1. You can verify these computations by computing cross product of these 2 lines. And then we will be transforming this line by multiplying this line with transpose of H inverse and you get the corresponding transformed line L prime. And H inverse in this case is given by this particular matrix. So, you know how to compute the inverse of a homography matrix or inverse of a 3 cross 3 matrix, and there you need to compute the determinant and you need to compute the cofactors, take the transpose of the cofactors, and then you have to divide the corresponding matrix by the determinant. You will get the corresponding inverse matrix. So, please go through a standard textbook of matrix operations. You will find out the steps of doing inverse, and you should be familiarized with these computations. Particularly since it is a 3 cross 3 matrix, it should not take that much of time to get an inversion. So, after performing the inversion of a matrix, transformation matrix, then you have to take the transpose of this matrix and perform the computations. So, if you do these computations, your line will come in this form. So, you can ignore the scale factor here. So, this scale factor you can ignore, you know that this it is same as representation of minus 49, 52, 27 column vector itself, and it will give you the similar equation of straight line what you have derived earlier also by the method 1 which we discussed in the previous slides. So, this is the equation of the straight line that you will get. We will continue this example by computing the vanishing line of in the transformed space. So, here as we discussed that vanishing line could be computed by transforming the line at infinity of the original projective space which is incidentally 0, 0, 1. So, we will be performing this computation, and if I multiply the corresponding transpose of this inverse with 0, 0, 1, then you will get the corresponding vanishing line as 5 minus 15, 5, and in the conventional coordinate representation, this would be equivalent to the straight line 5x minus 15y plus 5 equals 0. So, now we will study another interesting property of projective space, and we will see that projective transformations, they form a group. We call it a linear transformation, and this is a linear transformation, and we call that group as projective linear group. So, the essence of this property is that if I consider a transformation of a space to the points in the another space by the transformation H1, subsequently another transformation from this space to the third projective space by H2. Now, this is equivalent to transformation of the first to the third space directly by a matrix H, which can be derived by composing these two matrices H1 and H2 simply by multiplying these two matrices. This property holds because of this property of projective linear group. So, which means that a cascade of transformation can be replaced by a single transformation. That is one of the implications of this property. The other implication is that if I consider a series of transformation, suppose we are transforming first those points by H1, next the transformed points to another transformation space by H2, and from the third transformed space to a fourth transformed space by H3. Then by applying cascade, we can simply multiply all these matrices H1, H2, H3, and we can get the single transformation. We can equivalently represent it by a single transformation from the first to fourth space. But the interesting part is that, as you know, the matrix multiplications, they are all associative. So, it does not matter in which order you compute these multiplications. That means, we can compute these operations by first taking multiplications of H2 and H3 and then multiplying with H1, or first multiplying with H1 and H2 and then multiplying this matrix before H3. So, this will give me the composite matrix H. So, this is another property you can perform these compositions with different compositions, and this is possible because of that group property. So, there are some interesting structure in these particular groups, and we will see that there are subgroups and there is a hierarchy among these subgroups. So, our parent group is a projective linear group. So, all projective transformation they fall under this category, which is in general which is a projective linear group. As we have discussed all those properties are they hold for this kind of transformations. Now, there is a special case of projective transformation, and they are called affine projective transformations, and they form affine group. One of the key property of this particular transformation is that their last row should be 0, 0, 1. You can multiply with any scale factor of 0, 0, 1 also. So, it is very easily distinguishable. We can easily determine that whether the transformation is an affine transformation or not. Then a special class of affine group is called Euclidean group, when the upper left 2 cross 2. So, this is the upper left submatrix. This should be orthogonal. As I have told you, the bottommost row or the last row, it should be 0, 0, 1. They should have the value of 0, 0, 1 or a scaled multiplication of this vector 0, 0, 1. So, that forms the affine group, and a special class of affine group becomes Euclidean when this submatrix is an orthogonal submatrix. And finally, another subgroup which is also a special class of Euclidean group, which is called oriented Euclidean group, if the determinant of this submatrix is equal to 1. That means, upper left 2 cross 2 submatrix is equal to 1. So, we call that group as oriented Euclidean group. So, as I mentioned, as that oriented Euclidean group is a subclass of Euclidean group. Euclidean group is a subgroup of affine group, and affine group is a subgroup of projective linear group. So, we have this hierarchy in the transformation space. With this, let me stop for this lecture, and we will continue this topic in the next lecture. Thank you for listening.